Have you ever really, truly stopped to think about the world around you? I mean, the chair you're sitting on right now, it feels solid, doesn't it? Of course it does. Well, today, we are going to dive into an idea that is so mind-bending, it might just change the way you see everything. The idea that the solid world you see and feel, well, it isn't anywhere near as solid as you think.
So let's just start with the big one. Here's a question for you. Everything, and I mean everything, the device you're watching this on, the floor under your feet, your own body, it's all made of atoms. And we know for a fact that those atoms are almost entirely empty space. So if you and a solid wall are both over 99% nothing, then what in the world is stopping you from just passing straight through?
I really want you to grasp just how empty we're talking about. Imagine an atom is the size of a giant sports stadium. The nucleus, the dense part in the middle, that would be a tiny marble sitting on the pitcher's mound. And the electrons? They'd be like little specks of dust zipping around the highest rows of the bleachers. Everything else inside that entire stadium? Absolutely nothing. Pure empty space. And that is the reality inside every single thing you can see and touch.
Yeah, so this is what you could call the 99% empty paradox. And it's a real head-scratcher, right? It just goes against all our common sense. How can something be solid and almost completely empty at the same time? To figure this out, we've got to throw out that old idea of atoms as tiny little billiard balls bumping into each other. The real answer lies in the invisible forces and weird rules that are running the show.
You see, the secret to what we call solid isn't about filling up all that empty space. Not at all. It's actually about these powerful, invisible forces and a really specific set of rules. And to understand solidity, we first have to look at how matter interacts with something we see every single day, light. It all comes down to a tiny but incredibly powerful gatekeeper that decides what gets through and what gets blocked.
So who is this gatekeeper? Well, let me introduce you to the star of our show today, the electron. Now, don't think of it as just some tiny particle. Think of it as a bouncer, an enforcer of some very, very strict quantum rules. And this little enforcer is unbelievably picky about how it deals with the world. In fact, it's this pickiness that creates everything we see as solid or see-through. Okay, so the electron's pickiness all comes down to this thing called energy levels. And honestly, the best way to wrap your head around it is to picture a ladder. An electron can stand on the first rung, or the second, or the third. That's fine. But what it can never ever do is just hover in the empty space between the rungs. And for it to jump from a lower rung to a higher one, it needs a very precise kick of energy, no more and no less. Let's see this whole thing in action. Imagine a particle of light, a photon, comes flying toward an atom. The electron acts like a bouncer at a super exclusive club. It checks out the photon's energy. Is it the exact amount it needs to jump to the next energy level, the next rung on the ladder? If it's a perfect match, a precise fit, boom. The electron absorbs the photon and makes the leap. But if the energy is off by even the tiniest little bit, the electron just ignores it completely. The photon just sails on by as if nothing was ever there. All right, so that's the secret sauce. This whole picky electron rule is the key to everything. It perfectly explains the difference between something like a brick wall and a clear pane of glass. Why does light get stopped cold by one but sail right through the other? Well, it's a tale of two very, very different quantum ladders. So here's how it breaks down. In a material, like a wall, the rungs on that energy ladder are really close together. It turns out that the energy carried by visible light is a perfect match for lots of these little jumps. So, as light hits the wall, its photons get absorbed over and over again. The light gets blocked. The wall is opaque. Simple. But in glass, the very first available rung on the ladder is way, way up high. There's this huge energy gap. The photons in visible light, they just don't have enough juice to make that giant leap. So the electrons in the glass just ignore them completely, and the light passes right on through.
The big takeaway here, the really crucial point, is that being see-through has absolutely nothing to do with how physically dense something is. It's not about tiny holes in the material for light to sneak through. Nope, it's a quantum decision. It's an interaction based entirely on whether incoming light has the exact right key to fit the electron's lock. But hold on, because the story has one more layer to it.
Just when you think these rules are starting to make sense, quantum mechanics loves to throw a curveball. And the story of glass and light has this really fascinating twist, and it involves a type of light that we can't even see. And it proves, beyond a doubt, just how specific that perfect match rule really is.
Okay,
Here's a real-world puzzle you might have wondered about before. We all know that sunlight is what causes tans, or, sunburns. And we know glass is transparent. Sunlight comes right through it. So, why can't you get a tan sitting inside next to a sunny window? The answer proves our whole theory about that picky little electron.
And here's the secret. Sunlight isn't just one thing. It contains all the visible light we can see, but it also has higher energy ultraviolet light, or UV light. And it's that UV light that's responsible for tans. So remember, that big energy gap in glass, the one that visible light couldn't cross? Well, visible light can't make the jump. But the higher energy UV light, it packs a much bigger punch. Its energy is the perfect match to leap that gap. So the electrons in the glass eagerly absorb those UV photons, blocking them from getting through. That's why glass is transparent to our eyes, but it acts like a solid wall to those tanning UV rays.
So, let's bring it all back home. We've seen how the picky electron decides if light gets to an object. And believe it or not, a very similar principle is what stops you from walking through that wall. It's not that your atoms are physically bumping into the wall's atoms, not at all. It's that the electron clouds of your atoms get close to the electron clouds of the wall's atoms, and they powerfully repel each other. They push each other away with this incredible force, all without a single atom ever actually touching.
So what's the final verdict in all this? Well, these concepts we use every day, words like solid or transparent, they aren't really fundamental properties of things. They're just our descriptions of an outcome, the result of this invisible, complex dance between energy, forces, and those incredibly picky electrons. The world we see and touch and feel is just a translation of these deep quantum interactions into a language our senses can finally understand. This, right here, is the heart of it all. Solidity isn't something an object is, it's something it does. It's an interaction. When you press your hand against a wall, you are not actually making physical contact. What you are feeling is the immense electromagnetic force from the wall's electrons pushing back against your hand's electrons. It's an invisible force field governed by these strange quantum rules that's just so powerful it feels completely and totally solid to us.
And that leaves us with one last big question. If something as basic and fundamental as solid is really just an elaborate illusion created by unseen forces and rules, then what else that we take for granted about our reality is just a perception, just an interaction, and not at all the way things truly are?